Okay, now we're actually doing some real proof work for finding the derivative of a function. We're doing algebraically, and the answer that we get is going to be the exact derivative of a function. Um, so what we're going to start off with is looking at the derivative function of y equals x squared. So we've got our function f of x equals x squared, and we want to know what is the derivative function. Now, if you look back in what we did in the last day's work, we took the function x squared, we actually looked at this exact function, and we looked at all the tangent lines and approximated the tangent lines and got a good, we guessed or approximated, that the derivative function was 2x. And if you look back at those videos or the class notes from that, we did this. And we want to see, is this right? Is it exactly right? And the way that we're going to, what we're going to use now, what we're going to be using for the next bunch of days until we start generating some really helpful rules, is we use this limit definition of derivative right here. And just as a reminder of what this is, what we're doing is we're saying let's have some, our function x squared, and we're choosing any point A and some point h units away. So this new point would be a plus h. So this value is f of a. This value is f of a plus h. And if we were thinking about the rate of change between those, finding the slope of that line, the slope change y over the change in x, the slope would be f of a plus h minus f of a all over a plus h minus a, where in the denominator you have an a minus a, so they go away, and you're just left with h. And that's this piece right here. And then what we're going to do, if we're talking about the instantaneous rate of change at some point, any point A, well, the instantaneous rate of change is when h gets small. So instead of looking at, this distance here, let's look at a much smaller distance, a plus h. And let's let this distance between a and a plus h get infinitely close to 0. So let h get close to 0. And now, instead of looking at some specific point A, let's make it general. Let's say instead of looking at A, let's look at the point X. So let me go on to the next page. Let me make a new page here. So this is really important for your understanding of derivatives. So we've got the function f of x equals x squared. Now let's choose any point x and some point x plus h. Here's f of x. Here's f of x plus h. And the rate of change between them, so the slope of that line, is f of x plus h minus f of x. Now the difference between this page and the last page is that we're, instead of choosing some point A, instead of choosing some point A, we're keeping it totally general. We're saying like any point x and then some point that's h units away from it. And we're finding the slope between those. The x away. And what we want to do, if we're talking about an instantaneous rate of change, we're talking about we're letting h get really, really close to 0. So we're saying let, or the limit as h approaches, or sorry, not that, the limit as h approaches 0. So in other words, this distance approaches 0. This will tell us, this whole thing tells us the instantaneous rate of change. Or, in other words, it tells us the derivative. And just as a reminder, the derivative we write as y prime, as dy dx, as f prime of x, as d dx of f of x. So these are all different ways of writing the derivative. Okay, so this is all just kind of preamble to actually do the work. So I've got, once again, same thing. Y equals x squared. Choosing some point x and a point that's really close to it, x plus h. The instantaneous rate of change between them, we're going to calculate as the limit as h approaches 0 of f of x plus h minus f of x all over x plus h minus x. Okay, so you've seen me write this a bunch of times, and you're probably wondering, well, what do we do? What do we do? How next? So let's actually evaluate these functions, because my function f of x equals x squared. So if I evaluate this function, f of x plus h, we're putting x plus h into my function. So that's going to be x plus h squared. I just plug x plus h into x. And we get x squared, but instead of x squared, we have x plus h squared. Minus f of x. Well, f of x is just x squared all over h. And, again, where do these squareds come from? That's coming from my original function is x squared, and I'm evaluating it x plus h, and it's just x. The next step is to simplify. And when we simplify, things are going to go away, and we're going to get down to one really, really nice number. So we say the limit as h approaches 0. Well, okay, we need to expand that. It's a binomial expansion, x plus h squared. That's something that I expect you to know how to do pretty well. X squared plus 2xh plus h squared minus x squared. And again, this red piece is just the expansion of that binomial square. And it's all over h. So now let's simplify that. We have the limit as h approaches 0. Now, just as a precursor, we're letting h get close to 0. We can't just plug 0 in for h, because if we plug 0 in for h, we would be dividing by 0. So we can't just let h be 0. We can't let h be 0, because if we did, we'd have 0 in the bottom. But when we simplify this, so notice when we simplify this in this next line, we've got an x squared and a negative x squared, those go away. So we'll have just 2xh plus h squared over h. Splitting up the fraction, we have the limit as h approaches 0 of 2x plus h. Now, just to kind of spell that out, in the first fraction, the h's cancel off, and we just have the 2x. And then in the second fraction, we have h squared over h, so one of the h's goes away for each. Now we don't have h in the denominator anymore. So since we don't have h in the denominator, we can now let h approach 0. And when we do that, when we let h go to 0, we have 2x plus, well, now let's let h go to 0. 0. 2x plus 0 is just 2x. And what is that? That is my derivative function. And it's what I should expect. Because looking back at what we did yesterday, that's what our tangent line graphically approximated derivative function was. Also, thinking back on what we did the other day, we had a quadratic. We started off with a quadratic, and then my derivative function is linear. So we drop to power as we kind of are learning to expect. Okay, let's do another one of those. So now we're finding the derivative of y equals x cubed. Just for review, y equals x cubed looks like this. So we're choosing some point, in general, some point x, which corresponds to x cubed, given my function is x cubed, and another point, x plus h, which corresponds to x plus h cubed. And we're finding the instantaneous rate of change between them. So we have x plus h cubed, which is that, minus x cubed, f of x, all over x plus h minus x. And we want to let h go to 0. Because we want to get this, we want h going to 0 means that this distance gets real small, so that we're looking at the instantaneous rate of change. Okay, so this problem is just a little bit more tricky because instead of having a binomial squared, we now have a binomial cubed. If you're not familiar with Pascal's triangle in terms of binomial expansions, it's worth reviewing. It's worth coming up and asking me about it. But I'm assuming that you got that hammered in pre-cal in Algebra 2. So I'll just jump ahead and say that we can simplify this as x cubed plus 3x squared h plus 3x h squared plus h cubed. And that blue underline is just this expanded. And if you're not familiar with that, find me soon. Find a friend, look on Google, look on YouTube, and look up binomial expansion using Pascal's triangle, and it'll show up really quickly. So, and then we have this minus x cubed, and that's this piece here, all over h, because the x's go away. Simplifying this, we have the limit as h approaches 0. Well, x squared, negative x squared, they're going to go away. So we're left with 3x squared h plus 3x h squared plus h cubed all over h. And the technique is the same now. Let's separate these fractions, and then let's let h approach 0. So separating the fractions, if we look at the first fraction, that is 3x squared. The next fraction is 3xh. And the very last fraction is h squared. So now we've gotten h out of the denominator. And that's the important thing, because with h in the denominator, we can't let h be 0. But with h no longer in the denominator, now we can let h be 0, and that's what we're going to do. So this limit equals 3x squared plus 3x times 0 plus 0 squared, which simplifies to 3x squared, and that is our derivative function. Get that clearer. Our derivative function simplified to 3x squared. And once again,